So in this video, we're going to be looking at skeletal formula, the best way of representing our actual organic compounds in a written format, right? Now, skeletal formula is a simplified organic formula that's shown by removing all of the hydrogen atoms from the actual alkyl chains, leaving just a carbon skeleton and any important functional groups on there as well. Now, if we were to look at the first one, we've got hexane over here. Hexane itself, I can actually draw out the structure for the displayed formula, looks something like this, but of course it takes too long. What can we do instead? Well, we can actually get rid of all of our hydrogen atoms and we end up with something that looks like this. We've got 6 carbon atoms over here, so we know of course it's going to be hexane. Now the next thing that I can actually do is, of course, I can actually show the zigzag shape that you actually get, the tetrahedral shape around every carbon atom, because each carbon atom is going to have 4 bonded pairs, 0 lone pairs, all electron pairs repel, and we end up with that tetrahedral shape. So we end up with a structure that looks like this in terms of the tetrahedral shape if you got rid of all of our hydrogen atoms. Now if you look at it right, every actual corner and every actual edge will actually represent a carbon atom, and so what we can do instead is we can actually just draw a bunch of different lines where we've got over here 1, 2, 3, 4, 5, 6 corners and edges. So I know I've got 6 carbon atoms, and let's say if I were to find out the number of hydrogen atoms, which aren't that important, we can actually end up with however many bonds we've got missing to this little kind of corner over here. We can actually say we've got 3 bonds missing, so we must have 3 hydrogens. 2 bonds missing here, there must be 2 hydrogens there. 2 more here, 2 more there, 2 more there, and then we've got 3 bonds missing, so we end up with 3 missing hydrogens there as well. So that's what we can actually draw rather than writing out the displayed formula, and everyone understands this across the world, and it's what we prefer to do as chemists. Now what about if I'm dealing with something like 1-bromo-pentan-3-O? Well, in this case, of course, I would actually end up forming something that looks like this for the displayed formula, and I would do the same thing again. I would get rid of all of the hydrogen atoms that aren't part of functional groups, leave any functional groups that are there. I would form the zigzag shape, and then I would end up, right, again, just drawing some lines to represent the bonds. These are the bonds, and then of course the carbon atoms are going to be the edges and corners, but in this case we actually add on a bromine over here on this carbon atom, and then we've got a carbon oxygen double bond shown there as well. Now, how would I go about finding the molecular formula? Quite quickly, well, I would need to look at how many carbon atoms again I've got here 1, 2, 3, 4, 5, and then it's going to be 6 carbon atoms in total. I've got 6 corners and edges, so I know it's going to be C6 for hexane, and then I've got 1, 2, 3 bonds missing there, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and then 14 altogether. So I've got my formulas being C6, H14 for that one. Look at the next one. I've got over here this example again that we've already seen. We've got again bromine attached there, we've got oxygen there, so we know we're going to have oxygen and bromine there. But what about carbons? I've got 1, 2, 3, 4, 5 corners and edges, so I know I've got C5, and then I've got 1, 2 bonds missing there, 3, 4, then I've got 5, 6, 7, 8, 9 itself, so I've got H9. The reason why I ignored this one over here is because you've actually got already a double bond here, that's 2 bonds, then 3, then 4 bonds all together there. So yeah, I add on my oxygen and then I add on my bromine there as well, and there's that one done there. Now that's just one example of course how you can end up with functional groups on there, but there's multiple different functional groups that you can actually get. Your standard alkanes, they're just going to be of course straight lines. Your alkenes, you just end up with a double bond that looks like this, and your haloalkane is of course going to be your carbon atom is attached to a halogen like bromine over here. If you were to look at your alcohols, you've got an OH attached to that carbon atom over here. In terms of your branched alkanes, you just draw another line that comes out from it, and then of course your cycloalkane, in this case you would draw the shape. So in that case, if you've got a cyclohexane molecule, it would be a hexagon. If it's cyclopropane, it would be a triangle, and so on. In this case, we've got 5 carbon atoms because I've got 5 corners to this shape. I know it's going to be cyclopentane itself. If I were to look at the next one, I've got here cycloalkane, same thing again, but you're just adding that double bond in there to show you've got an alkene. Amines would look like this. If you were to look at your ketones, again, carbon oxygen double bond is not at the end, whereas an aldehyde is at the end itself. If you were to look at a carboxylic acid, you've got your carbon oxygen double bond at the end, but you've also got an OH on there as well. So these two, again, they're pretty similar, but in one way they're different with that OH itself. Esters, of course, it's when we have the hydrogen, and that's going to be replaced by some sort of an alkyl group. So I've got here technically basically it's going to be CH3 there itself. So moving on, I've got 2 examples for you to try. Feel free to pause the video, have a go at the following 2 and resume once you're ready to go over the answers. So yeah, looking at this one over here, I've got 3 carbon atoms, so I'm going to have 3 corners and edges for my zigzag, and then I can see at the end on the 1 position I've got an OH, so I'm going to draw a line going from that corner there, and I've got an alcohol here itself, and there's that one done. Nice, quick and easy. Look at the next one, I've got an aldehyde over here. You can see that I've got 3 carbon atoms again, so I've got 1, 2, 3 carbon atoms over here. You could have actually drawn it the other way, where you would have gone zag-zig instead of zigzag, so you might have drawn something like this, and you could actually end up with your carbon oxygen double bond. It can go like this, it can go like this, doesn't really matter, it's the same thing again. You might actually end up with, in some cases, your molecule, if it's flipped around some more, you could end up with something that looks like this as well. Either one of these, they're all going to be right themselves. Just like in propan 1-ol, you can actually end up with, of course, your zigzag, and you could end up with your alcohol going this way as well. Either one of them are going to be right. So yeah, moving on, another one for you to try. Pause the video, have a go, resume once you're ready to go over the answer. So yeah, looking at this one over here, longest carbon chain in this case is 1, 2, and then it's going to be 3, 4 carbon atoms, and then we've got to say, of course, we've got butane, so we've got 1, 2, 3, 4 edges and corners. On the second one, I've got chlorine, so that's going to point upwards in this case, and then on the third one, I've actually got a methyl group, so that's going to be, of course, a line on its own pointing downwards itself, and there's that one done. Now, of course, you could have got it flipped again, but of course, if you name it and you end up with the same name as the displayed formula, that's how you know it's right. Look at the next one, you've got 4 carbon atoms, 1, 2, and then it's going to be 3, 4, and then you're going to have, of course, a carboxylic acid. Now there's 2 ways again, more than 2 ways to draw this, but I'm going to show you 2 ways just in case. You end up with 1, 2, 3, 4 carbon atoms there. You're going to end up with, of course, your carbon oxygen double bond, and then you've got your OH like this. Or what you could have ended up with is, of course, if you went zag-zig for whatever reason, you might have ended up with 1, 2, 3, 4 carbon atoms there, and your carbon oxygen double bond is going to point downwards instead. So yeah, you can see over here, I've got my first 2 parts of the structure. If I add a chlorine, you add it onto the second carbon atom here. And then if I were to move this structure ever so slightly to the side, on the other one, you would end up with a chlorine on the second carbon atom again. It's the same thing, but you've just drawn it from a different angle. What about the next thing? Well, we've got, of course, here a methyl group next, and then we've also got an OH. Now, let's say if you've got 1, 2, 3 carbon atoms, you can kind of see over here that you've got 3 carbon atoms bonded. It would follow some sort of a hexagon, which it does. Now let's say if you've done 3 bonds to this carbon atom over here, the 4th one would actually go into the actual hexagon itself. So yeah, you end up with something that looks like that. So yeah, my oxygen is going to be bonded. Need to make sure that oxygen bonds to the carbon. You end up with something that looks like that. I could do the same thing over here again. Might just flip it for the sake of it. I end up with, let's say, a methyl going upwards this time, and an oxygen coming downwards in this case. So again, here you've got the same structure essentially. You've got 2 different ways of drawing it though. One of them is, of course, zag-zig, and one of them is going to be zigzag. Doesn't really matter as long as you name it and it comes out as the same thing. So yeah, moving on then, if we were to try some more difficult ones, I've got here some skeletal formula structures for you to draw from the name in this case. Again, it's a lot faster compared to displayed formula. Pause the video, have a go, resume once you're ready to go over the answers. So yeah, I've got here propan 2-ol. The stem, first of all, is 3 carbon atoms, and the OH is going to be at, of course, the second position. Remember, the carbon bonds to the oxygen. If you were to draw something like this, that would not actually be accepted. That would be wrong, because it's going to the hydrogen here instead. So there's that structure there. If you were to draw it zag-zig instead of zigzag, you would end up with something that looks like this instead. Look at the next one. You've got 2,2-dimethyl pentane. So you've got 5 carbon atoms, 5 sharp edges and corners. On the second position, you end up with a methyl, and on the second position, you end up with another methyl as well. But of course, remember, that's right, but you could have labeled it from right to left as well and drawn pentane out like this again, and you could have said that one's 2 as well. As long as you name it, it comes out the same, it's going to be right. Look at the next one. You've got 1,2-dichloropropane over here. Looks like this. You're going to end up with, on positions 1, you end up with a chlorine. Position 2, you're going to end up with a chlorine there as well. Again, you can flip it just like how I did with B. Look at the next one, you've got 2-hydroxypropanoic acid. So you're going to end up with 3 carbon atoms like this to an OH, and a carboxylic acid group is made there. And then you're going to end up with at the 2 position an OH itself that looks like this. If you were to draw it another way, you could have gone zigzag instead of zag-zig, and you would end up with, of course, the following, which is what I prefer, where your carboxylic acid, the O points upwards. You end up with an OH here, and then an OH over here as well. So either one of these two, they're going to be, of course, right. So yeah, moving on, I've got some more examples for you to try. Pause the video, have a go at the following, resume once you're ready to go over the answer. Now this next one, we've got hex and we've got cyclo. So that means, of course, we're going to have here a hexagon that looks like this. And then we're going to end up with, of course, an alcohol. That OH is going to be attached anywhere, because anywhere is going to be position 1 if you've only got one group attached. So yeah, there's that one there. If we were to look at the next one, we've got 2-bromopropanol. So in this case, we've got 1, 2, 3 carbon atoms. We've got an aldehyde at this last position over here, or the first one, and then a bromine at the second position over here. Now, of course, you could have drawn it the other way. So you could have gone zigzag, or you could have flipped it all together. So I'm going to draw it like this, the proper way, where I end up with carbon-oxygen double bond here, and then I end up with a bromine over here as well. So either one of these two are going to be right. Look at the next one. You've got hex. You've got 6 carbon atoms, 1, 2, 3, 4, 5, 6 carbon atoms there in total. On the 1 position, I'm going to go from right to left in this case. I've got chlorine, and then I've got a methyl at the second position, and then I've got an alcohol on that second position as well. But of course, you could have flipped the entire molecule. As long as you name it, it's the same thing. It's going to be correct. Look at the next one, a tricky one over here. We've got but2-ene-1-ol. Now this, we can see we've got an alcohol at position 1. We've got an alkene at position 2, an unfamiliar example that's come up on the exam before. You've got 4 carbon atoms in total. Alkene is going to be, of course, at position 2 in this case, and we're going to end up with an alcohol that's going to be at position 1. So we end up with something that looks like this itself, but remember, the OH could be here, or it could actually be on the other side itself. How can you check if it's right? Well, again, of course, you would name it. So either one of these two, they're going to be correct. So moving on then, I've got another example for you to try. I want you to name these systematically using our UPAC nomenclature. So something that we've done in the previous video, but we're just applying it to skeletal formula. Pause the video, have a go at the following, resume once you're ready to go over the answers. So yeah, in this case, we've got here 4 carbon atoms as our longest carbon chain. I'm going to number it from this side over here, and I end up with 4 carbon atoms there. Position 2, we've got this methyl here. So we know we call this one 2-methyl, and then it's going to be, of course, 4 carbon atoms, so it's going to be butane itself. Look at the next one. You've got 1, 2, 3, 4, 5 carbon atoms. So you know it's going to be cyclopentane. You've got an alcohol at position 1, we will say. We've got cyclo, and then it's going to be pentan, and then it's going to be, of course, 1, and then it's going to be ol itself, and there's that one done. Look at the next one. You've got an alkene. Again, we're going to start numbering it from left to right because that's the side the alkenes are. We've got but1-ene in this case. Nice easy example again. Look at the next one after that, bit trickier. We've got 1, 2, 3, 4 carbon atoms in total. I'm going to start on the side with the carboxylic acid. We've got chlorine at position 2, carboxylic acid at position 1. So in this case, I'm going to call it 2-chloro, and then it's going to be, of course, butanoic, and then it's going to be acid itself. And there's that one done. So yeah, moving on, I've got here the same task again. Again, you're going to try it, but this time you're also going to work out the molecular formula of the compounds as well. So yeah, in this case, we've got here the longest carbon chain. I'm going to start from this side. It's 1, 2, 3, 4 carbon atoms. We've got a methyl here, methyl there at the 2 position. So we would actually call it 2,2, and then it's going to be, of course, di, and then it's going to be methyl, and it's going to be butane itself. And there's that one done. What about the actual molecular formula? Well, again, we've got 1, 2, 3, 4, 5, 6 corners and edges, so it's C6. Now, of course, I could just use the alkane general formula because it would work here. Double it, add 2, you end up with 14. But if I count it, I've got 1, 2, 3 bonds missing there, 4, 5 bonds missing there, 6, 7, 8, 9, 10, 11, 12, 13, 14 hydrogens there because I've got 14 bonds missing. So it's going to be C6 and then it's going to be H14 there as well. Looking at the next one, we've got a similar type of thing over here. We need to find, of course, the longest carbon chain. It's going to be 1, 2, 3, 4 carbon atoms, methyl there, alcohol there. So it's going to be, of course, 2, and then it's going to be methyl, and then it's going to be bute, because there's 4 carbon atoms. It's an alcohol, so we say it's going to be an, and then it's going to be, of course, an alcohol. So we've got 1 ol in itself. We've got 2 methyl, butane, 1 ol. There's a name done. What about the formula? Well, of course, if I've got over here 4 carbon atoms, 1, 2, 3, 4, and then the 5th carbon atom over here, that's going to be C5. And then if I were to look at the hydrogens, I've got 1, 2, 3, 4, 5, and then I've got 6, 7, 8, 9, and then I've got 10, 11, and then I've also got 12 over here as well, H12, and then don't forget the oxygen, that's over here as well. There's that one done in terms of the molecular formula as well. Look at the next one. We've got our cycloalkene that's branched over here. I'm going to start numbering it from this side over here where I've got 1, 2, 3, because the branch comes at 3 this way and the alkene comes at 1. If I went the other way where I went 1, 2, and then 3, 4, 5, the branch would actually come at the 5th position, and that's what we don't actually want in this example itself. So yeah, if I were to number it the light blue way, I've got 1, 2, 3, then 4, 5. We know in terms of a prefix, we actually end up with, in this case, it's going to be 3 methyl, because I've got that alkyl group there. I'm going to have, of course, cyclo that comes after it. Remember, cyclo is going to be a part of the stem. It's not really a proper prefix, so we don't actually put it in alphabetical order like that. And then it's going to be, of course, pent, because I've got 5 carbon atoms, and then it's going to be 1 ene itself. Because there's more than one functional group or branch on there, we need to actually include numbers in this case. What about the actual formula? Well, I've got 1, 2, 3, 4, 5, 6 carbon atoms here altogether. And so in that case, I would have C6. What about the hydrogens? 1, 2, 3 there. We've got 4, 5, 6, 7, 8, 9, and then 10 over here. Don't forget the alkene. You've got H10, and then that's pretty much that example done itself. So yeah, there's the answer to that one. Look at the next one. We've got here pretty much just cyclohexene. That's the name of it. Don't need to highlight any positions because, of course, there's no other branch on there to compare it to, and the alkene will always be position 1. If you put cyclohex 1ene, that's fine as well. The examiner tends to just ignore it. But of course, there's the name. What about the structure? Well, of course, we've got 1, 2, 3, 4, 5, 6 carbon atoms for the molecular formula. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogen atoms altogether. So there's our molecular formula as well.